Has the mystery of the Hubble tension finally been solved? One of astrophysics' greatest dilemmas is the universe's expansion rate, which exceeds theoretical predictions. However, scientists from the May 6th have uncovered a crucial piece of the puzzle. Their research suggests that the Milky Way resides in a vast cosmic void, an unusually empty region of space. Interestingly, when an alternative theory of gravity is introduced, the discrepancy between predicted and observed expansion rates seems to disappear. But there's a major catch. This bold hypothesis challenges the very foundations of a standard cosmological model. What has long been part of the basics of astronomy today marked no less than a profound paradigm shift about 100 years ago. For generations, researchers of the past were convinced that the cosmos was a rigid, unchanging construct. Even a certain Albert Einstein initially held on to the idea of a static universe to such an extent that he added a cosmological constant to his equations, a step he later regretted as the greatest folly of his life. And although the young Belgian priest and astrophysicist Georges Lemaitre had already shown Einstein in 1927 how a mathematical model describing an expanding universe could be developed from the general theory of relativity, Einstein dismissed this concept as a mere mathematical gimmick. In retrospect, however, we know that Lemaitre's findings had a decisive advantage. After all, they made a prediction that could actually be observed. Specifically, it bridged the gap between the expansion of the universe and the light from galaxies. If the universe is genuinely expanding, distant galaxies should be receding from us, much like how dots on an inflating balloon move apart. Likewise, as light from these galaxies journeys toward us, its wavelengths elongate, causing a shift toward the red end of the spectrum. In the late 1920s, American astronomer Edwin Hubble verified this effect. By carefully studying numerous galaxies at the Mount Wilson Observatory in California, he observed that their light was redshifted, offering definitive proof of the universe's expansion. This discovery also led to a profound realization. If the universe is continuously expanding, then tracing this process backward suggests it must have originated from a single, incredibly dense point. This idea now forms the foundation of the Big Bang theory. By the 1990s, astronomers uncovered yet another surprising fact. Not only is the universe expanding, but the rate of expansion is accelerating. Scientists attribute this acceleration to dark energy, an enigmatic force believed to counteract gravity and drive the cosmos apart at an ever-increasing pace. The enigmatic Hubble tension presents a fundamental question about the universe's expansion. Why is it occurring faster than expected? At the heart of this cosmic mystery is the challenge of accurately determining the expansion rate. Theoretically, this rate is represented by the Hubble constant, but in practice, its precise measurement has produced conflicting results, collectively known as the Hubble tension. According to the Standard Model, the Hubble constant is estimated to be around 67 kilometers per second per megaparsec. To put this into perspective, 1 megaparsec MEAP is approximately 3.26 million light-years, with each light-year spanning 9.46 trillion kilometers. This implies that galaxies move away from each other at an increasing speed of 67 kilometers per second for every 3.26 million light-years, amounting to an astonishing 244,000 kilometers per hour per megaparsec. However, observations suggest it can be significantly higher. Direct astronomical measurements using supernovae, gravitational lenses, variable stars, and red giants indicate a Hubble constant of 73 kilometers per second per megaparsec, translating to 264,000 kilometers per hour per megaparsec. This results in a striking discrepancy of 20,000 kilometers per hour per megaparsec, highlighting the unresolved tension between theoretical predictions and observational data. How can this significantly higher value be explained? Could previous studies have been affected by measurement errors? This question was addressed by the James Webb Space Telescope when it re-examined data from the Hubble Space Telescope. A research team, led by Nobel Prize-winning physicist Adam Rees Q1, analyzed Webb's data from the past 2 years. Given Webb's vastly superior capabilities compared to its predecessors, Experts describe it as providing a high-definition view of the universe. Webb's data provided a precise confirmation of the Hubble tension. The most extensive Webb dataset to date, including supernovae, variable stars, red giants, and carbon-rich giant stars, confirmed that the universe is not behaving as expected. The latest analysis calculated a Hubble constant of 72.6 kilometers per second per megaparsec. According to Rees, the discrepancy between the predicted and observed expansion rates suggests that our understanding of the universe is still incomplete. One possibility is that an overlooked factor provided an unexpected boost to the early universe after the Big Bang. Alternatively, dark energy may be evolving. Perhaps it is denser or more intense today than in previous cosmic eras. However, scientists are also considering alternative explanations beyond dark energy. One intriguing hypothesis suggests that the Milky Way, including Earth, could be situated within an enormous cosmic structure known as a supervoid. To grasp the nature of this immense void, we must first revisit the large-scale structure of the universe. As widely known, stars and planetary systems exist within galaxies, which themselves cluster together to form galaxy clusters and, in turn, superclusters. For a long time, scientists considered superclusters to be the largest cohesive structures in the cosmos. However, extensive surveys later revealed that these superclusters are not randomly scattered, but are instead arranged in a vast, web-like pattern. This cosmic lattice is composed of long, thread-like structures called filaments, which can stretch hundreds of millions of light-years across. At the same time, these filaments enclose enormous, nearly empty regions known as voids. Despite the dazzling display of celestial bodies in the night sky, some researchers believe that these vast, seemingly vacant spaces constitute the majority of the universe. In numerical terms, it is estimated that between 50% and 90% of the cosmos is dominated by these immense voids, largely devoid of matter. A study led by Sergei Marrow from the University of Bonn suggests that cosmic voids might directly contribute to solving the mystery of the universe's expansion. Conducted in collaboration with researchers from the University of St Andrews in Scotland, the study is based on new observations indicating that Earth resides in a region of space with relatively low matter density, similar to an air bubble in a cake. As a result, the surrounding matter is denser, generating gravitational forces that pull galaxies within the void toward its edges. This seemingly straightforward concept implies that galaxies are receding from us faster than expected. In this context, variations in the Hubble constant can be attributed to this local underdensity, a simple yet significant explanation. However, there is a fundamental issue. The standard cosmological model does not account for such voids, as it assumes a uniform distribution of matter and space. How, then, can we account for the galaxies located 600 million light-years away that were examined by another research group and found to be receding at speeds 4 times faster than what the standard cosmological model allows? This puzzling observation challenges our current understanding of cosmic expansion and raises fundamental questions about the nature of gravity itself. Addressing this issue, Pavel Kupa, a researcher who also contributed to the study on cosmic voids, highlights a critical point. The standard cosmological model is fundamentally built upon Einstein's theory of gravity. However, it is possible that gravitational forces do not function exactly as Einstein originally proposed. In an effort to explore this possibility, research teams from the Universities of Bonn and St Andrews incorporated an alternative gravitational framework into their computer simulations. This alternative theory, known as modified Newtonian dynamics (MOND), was first introduced nearly 4 decades ago by Israeli physicist Moti Milgram. Though still considered a controversial or outsider theory in mainstream cosmology, MOND offers a strikingly different perspective on gravity. One of its key predictions is the existence of vast, empty voids in the universe, regions largely devoid of galaxies. This prediction is particularly significant because, if gravity indeed behaves in accordance with Milgram's model, it could provide a natural explanation for the anomalous galactic motions observed. In fact, undermined the long-standing Hubble tension, an unresolved discrepancy in measurements of the universe's expansion rate, would disappear entirely. If validated, this would represent a major shift in our understanding of fundamental physics and cosmology, potentially reshaping the way we perceive the large-scale structure of the universe.